So now let's go ahead and practice a problem. Problem 1 states, it would seem that there is an equally likely chance of being born in any month. To make this study a little easier, let's divide the year up by seasons, where winter will be January, February, and March, spring will be April, May, and June, summer will be July, August, September, and we'll end with fall being October, November, December. Below are the birth months by season for 80 individuals. Use alpha equals 0.05 to test the claim that a person's birth month comes from a uniform distribution. So the first thing we need to do is state H0 and H1. So as we reread the question, it says to test the claim that a person's birth month comes from a uniform distribution. Now we could write that exactly as we see it, but because I wanted to focus on the fact that H0 deals with equality, I've rewritten it to read, birthdays appear with equal frequency in each season. But if you had just written person's birth month comes from a uniform distribution, that would have been perfectly fine. So now I need to have not equals or inequality in H1. So therefore I've written birthdays appear with unequal frequency in each season. Or if you had gone with the way it's written, I would say that a person's birth month does not come from a uniform distribution. So first I'm going to find the critical value since that's a little bit easier. So remember, we need to figure out which row and column we're going to. And so we're going to go to row 4 minus 1, which is 3. But wait a minute, we said 80 people's birthdays were selected. So why am I saying row 4? Well, if you remember, 4 is the number of seasons, not the number of birthdays. The N for a goodness of fit is based on number of categories, and we only had 4 categories. In terms of the column, we're going to go to alpha equals 0.05, which came from the question. Remember, we do not divide this by 2, even though not equal to is our null hypothesis. Alternative hypothesis. I guess I'm having a hard time with that one today. So we treat it as a right-tailed test, even though H0 and H1 look like a two-tailed test. And so I'm using the table, and I look it up to find 7.815. So the next thing I need to do is to find the test statistic, and we just went over that formula. And the first thing I need to do, though, for that formula is figure out what is my expected value. Well, to do the expected value, I need to figure out how many items, data points, were collected. Now, our question did say there were 80 people or 80 birthdays collected, but if you'll also notice that if I add up the observed per category, I'm also getting 80. So this way, if it doesn't come in the question, that's where you're going to find it yourself. So now we can say that 80 birthdays. So now we can say since 80 people were surveyed, if they had an equally likely chance in being born in any of the how many seasons? Well, we just talked about that up above. So any of the 4 seasons listed, then we would expect that 80 divided by 4 equals 20. So we're expecting that if this was a uniform distribution and we sampled 80 people would have been born in the winter, 80 in the spring, 80 in the summer, 80 in the fall, etc. I keep saying 80, but it's 20. Oh my God, sorry. So now I can go ahead and work on finding the test statistic. I need to subtract the observed from the expected and square and continue to do this for each of the observed and expected values. But instead of writing it out like this every time, maybe you just start with doing the subtraction, observed minus expected, to get, -5, +1, etc. Now they're going to be squared. They haven't been squared yet, but I thought it might be easier to write it now. Notice that observed minus expected will always add to 0, unless you maybe have a rounding error. So now I can actually square those values, which I didn't need a calculator for. And again, instead of writing each of these new values divided by 20, whenever you're adding fractions with the same denominator, then really you just add the numerators, which in our case is 52, and now I can divide by the denominator to get a test statistic of 2.6. So now we're ready to make our final decision. We've already looked up our critical value and just finished calculating our test statistic. So I'm going to go ahead and look at a curve with those values. Now, because it's the chi-squared table, I know it's a right-skewed graph, but really it's not the curve that matters. It's the numbers we write on the bottom. 2.6 is the test statistic. 7.815 is the critical value. On a number line, this is the order they go. As always, I like to label them to make sure that when I'm finding my critical region, I'm shading from the correct number. We shade from the critical value always to the right for a goodness of fit test. And so the test statistic does what? It does not fall in the critical region, so we fail to reject H naught. Now, we'd already decided that H naught was the claim because it said test the claim that birthdays come from a uniform distribution. That was equality, which is H naught. We just said we failed to reject that. So our conclusion would read, there is not sufficient evidence to warrant rejection of the claim that a person's birth month comes from a uniform distribution. Now I kind of flip-flopped. I went back to what was written in the sentence, not what I wrote for H1. There probably should be consistency, but I was just trying to show a variety of ways to do this. And also, we just in chapter 10, we're working on tables to organize our data. Maybe you want to do that here. The formula is to add up all of the observed minus expected squared divided by expected. So why not just once you figure out what the expected is, you could fill that into a table. You could then subtract the observed from the expected. You could then square all of those values. Oops, I forgot. Don't forget that should total 0. I don't know how many people check it, but now I'm going to go ahead and square. And again, we could divide by 20 the expected, or we could just add them and then divide, because only when all of the expected are the same. So I got a total of 52 divided by 20, which is the same test statistic.